Good. Hello, good morning, Happy New Year. Yeah, the rest will come. There's snow in Germany, and so there's a lot of snow, and that's why everybody will come 7 minutes late. Anyway, so we start at 8 here, also in the new year. So this is so we're starting today again with statistical methods. So I will always start with what I think is more demanding on the specific weekday, on the specific day. And today, for me at least, the statistical methods bit is a little bit more demanding. And this is the overview of what is to come in the second half. Hello, can you please come like 5 minutes before 8 and not exactly at 8 because it's a little bit annoying. Happy New Year, by the way. So the second half of the winter term is dedicated to the GLM for FMI, and we started with that before Christmas, and as you remember, and then the remaining program now until the mid of February is the following. So we start today talking about first level design regressors, specifically the convolution approach. Then we talk a little bit more general about first level designs and discuss one way to look at their efficiency. Then the next chunk will be devoted to ANOVA and ANCOVA designs with the aim of talking about PPI, so psychophysiological interaction analysis, which I hope you've seen in some papers previously. And then the last bit, so there are 3 bits if you want until the middle of February, we talk about how to, the spatial aspects of the whole thing, how to evaluate significance essentially in fMRI research. So that's the plan. So essentially talking about design matrix formation, then talking about so design matrix formation for kind of any kind of design that worked with this onset convolution approach, then talking about a specific design with some idea about connectivity, PPI, and then talking about p-values in fMRI. So that's the plan, and then the next step then will be these exams in February or April. Yeah? Any questions about this? No? Good. Then let's start with Mickey Mouse and then some GLM stuff. So,
one question.
Yeah.
So we're having a statistics class now.
Yeah. Yeah, so as I said at 8, so I'm switching back and forth because one thing is always more demanding than the other on a given day, cognitively demanding, and I'm starting with the one that is cognitively more demanding because that's then easier for me. So when later I get hungry and so on, then I do the stuff that is less cognitive demanding for me and maybe also for you. So any questions? No, good. So what I want to discuss then is what is called in the PMFN book first level regressors. And what is in our outline is called convolution. So that's the same thing, roughly. And I want to start with a little bit of a review of the GLM and also to see where you are up to. So before Christmas, we introduced the GLM, and I obviously always ask you to also look into the GLM lectures and the stuff that you have. And this is, in a way, the fundamental equation that describes the GLM not only for fMRI, but also for fMRI. And when we talk about fMRI, or we are talking about fMRI, so this is what I want to then remind you of. So here this P, what does the P mean?
Sorry, I didn't pay attention.
Well, that's not very good. So the P, what does the P mean? Exactly, very good. So this P refers to a probability density function. This whole thing describes a probability density function over Y. What is Y? Sorry? Well, okay, yeah. So it's a probability density function that is written down here, and the Y is in the domain of the probability density function. That is definitely correct. But what does it model in terms of fMRI? So what is the Y when we talk about fMRI? The signal, and what exactly? So can you say a little bit more about the Y? So it's definitely the MR signal, but is it of all voxels, of a single voxel, and how many values are there, and so on?
The image of the voxel? The image of the voxel?
The image of the voxel, well, it's the time series of the voxel. Can you say a little bit more about the Y? What the Y is?
Well, it's the time series of a single voxel.
And in mathematical terms, so what is the Y? Is it a matrix? Is it a complex number? Is it a vector? It's a vector. And how many entries does it have?
N entries.
No, I mean, that's one could use any label, but N is the one that we always use. So there are N time points, which refer to the images of that are acquired during a single run, and what this whole thing then is a voxel time series. So very good. So this is so what we're describing here is the a probability density function over vectors that model the MR signal time series of a single voxel. And then let's go on. What's the N? Alexander, I think is the name. What does the N refer to?
But it's normally distributed. It's Gaussian.
Yeah, that's the Gaussian. Is it what kind of Gaussian distribution is this?
No, it's
well, it's not univariate, so it's
multi.
exactly, yeah. So it's a multivariate Gaussian, and of course it's a n-dimensional Gaussian because the data is n-dimensional. And then this notation, basically, I mean, this is just a short notation for the functional form that we looked at previously, that has the exponential and the dot product of the data minus the expectation in it, and so on. So this is the short form, but it shows all the main ingredients. So Y is again the data, just as a reminder. But then we have this X better. So what is X, Aline?
X is the matrix.
Yeah, it's a matrix. How's it called? This matrix has it's the design matrix. Very good. And what is the dimensionality of this design matrix?
N times P.
Very good. So that's N times P. And yeah, so what are the what is in the design matrix? I mean, this is basically the topic of the next weeks, but do you remember from our intro? The regressors, yeah, essentially, and how these regressors are formed. This is what we'll talk about next. Okay, then better. We have enough, you don't get anything. Yeah, what do they encode and how many are there?
As many as there are conditions.
And in terms of, if you look at the design matrix, how many conditions are there? Almost P. So because this is a matrix product, so you always need to look at the inner dimensions, and this is P times 1. And what do the beta parameters refer to, or what do they quantify? What do they encode? No. So they encode, if you think about the linear combination, how the design matrix columns are added to reproduce the time series, these beta parameters. They quantify the contribution of each regressor. So they are the effect size. If you are happy with calling beta parameters effect size and not necessarily always think about Cones D, which is the beta parameter divided by the standard deviation. So this is quite important because they are kind of one of the most important things in terms of inference. So they quantify how much each regressor contributes in the generation of the signal. So try to be clear about the beta parameters. Sigma square, what is that? Yeah, it has to do with the error. Yeah, it has to do with error. So that's kind of going into the right direction. So that's the variance parameter, and it quantifies the size, or the variability, the size, the magnitude of the noise. So this model obviously tries to make a deterministic prediction based on X beta, and it allows for some stochastic deviations from that, and the sigma square quantifies the size of this stochastic deviation. If you estimate it, then of course it refers to the residuals. So that's the variance of the error if you also write this separately. So this is this first chapter in PMFN on GLM and notation, where the relationship between the error, if you look at it as an additional additive error term, and the variance of this Gaussian is made explicit. Okay, used to remember your name, I've forgotten it again. IN, what is IN?
The identity measure.
And what does it encode? Why is it there?
Well, it only has one solid diagonal.
That's how it looks.
So it only has, so the whole matrix for the errors only has the diagonal and only the variances, but not the covariances.
So if there are no covariances between the error terms, what does that mean? Yeah. So that's the important thing, that the spherical covariance matrix, as this whole thing is called, encodes. So there are independent error contributions. So the error that is added to the value that is predicted by the model at time point 10, and the error that is added to the prediction of the model at time point 11, they are independent. Which which is somewhat violated by time series data, which is why there are more advanced covariance models usually used, but I don't think we will discuss that in detail. So if you have some time between time points, then it might as well be okay to look at them as independent. Yeah, very good. That was surprisingly good, actually. So you know roughly where we are and what we're talking about. Very good. So then the big topic for the next 4 sessions is actually the design matrix and forming the regressors of the design matrix. So that's the stuff that we then want to discuss at least the next 2 weeks. So let you get an idea about that. And we discussed that previously. So does anyone remember how the columns of the design matrix are formed? I mean, we looked at that visually, and so does anyone remember that?
I'm not sure if that's what you mean, but I think it was always like time point 1, condition 1, time point 1, condition 2, time point 1, condition 3.
Yes.
It's like the first line, and then time point 2, condition 1, time point 2, condition 2, time point 2, condition 3.
Yeah, that's correct. This is how this is encoded essentially in the entries of the design matrix. But from an fMRI perspective, when you do an experiment and then create a design matrix to analyze some data, and maybe if you think about these pictures that I've shown you with respect to the master univariate approach, or if you ever read an fMRI paper and somebody tells you how they did their GLM analysis, does anyone remember the keywords there, how the GLM regressors are formed? No? Maybe I try to remind you of something. So do you remember these kind of stick functions? So what were those? How did we call them? We looked at these pictures. I made beautiful pictures. Let's show you the pictures. So the new pictures. So these pictures here. Do you remember what these pictures were about? Or what these stick functions were about? Exactly. So this would be one condition. On the x-axis we would have time. And so if this is one condition, for example, I don't know, phased presentations or computing the sum of 2 numbers, or remembering what you did on Christmas versus what you did at Easter or whatever. So these are the time points when people perform a cognitive task, and they are usually called onset times. I try to call them event onset times now all the time, although they're often called stimulus onset times. But of course you can also have events that are not given by external stimulation necessarily. So that's why I try to call them events and not always stimulus onset times. Yes, so these are the onset times that you record when you do your experiment. So you present something to the participant and basically turn on the stopwatch to make sure that you know when, with respect to the data acquisition, you presented a certain condition. And what happened then before these were entered into the design matrix? Want to remember that? Yeah.
There was this function, but I don't remember how it's called, but it kind of simulated how neurons would react.
Neurons or?
The MR signal.
Yeah, the MR signal, but in terms of the biology. The hemodynamic response function, or the hemodynamic response.
And the thing that, like on every onset of each event, map this hemodynamic function to.
Yeah, I mean that's what we can say. So or at least that's what you can say up to today, because today you will learn more about this. But this is how we discussed it previously. So essentially, we said, okay, if we want to use somehow these onset times and create a model that predicts an MR time series, we know that the response to a simple stimulus, a simple visual stimulus, has this hemodynamic response function shape. Maybe with an initial dip, maybe not, maybe with a post-stimulus undershoot, maybe not, but definitely with a peak. And then the way we discussed that previously was essentially that these stick functions or onset functions, which are just once at a given entry or time point of these time vector from the beginning of the experiment to the end of the experiment, they are just replaced by these hemodynamic response functions. So roughly this would look like this here, because they are 4. And this is what I had shown you with this picture. So essentially, from these conditioned stimulus onsets, one goes by means of convolving the stimulus onsets with the hemodynamic response function, which is a model of the hemodynamic response, to these regressors or predicted MR signals, which then correspond to the columns of the design matrix. So this is as far as we went with this previously. And then today, I want to talk more about this process here, this convolution process. You might remember, and I hope you do remember, because there will be an oral exam on this soonish, that we also discussed the bold signal or the MR signal as a linear time invariant system in our introduction to fMRI. So that there was this, that there were these experiments in the late 90s that checked whether the bold system or the whole system from stimulus to brain or neurons to neurovascular system, hemodynamic response to MR signal, behaves as a linear time invariant system. So we looked at that in the other course. And this linear time invariant system behavior and the idea that you can essentially do this and create a meaningful regressor, this is tightly interlinked, and this is what I want to discuss today. So essentially, the basic story here is that if you use convolution, so if you use this approach of convolving your event onset times with the hemodynamic response function to get a predicted MR response as a regressor in your design matrix, what you implicitly assume is that the whole system of the brain, then its neurovascular coupling and the MR signal acquisition is a linear time invariant system. And this is what I want to make explicit today, and in this kind of context, also then discuss convolution in a little bit more detail. Yeah. So this is the topic. So essentially, how to go from here to here. This is the topic. The next topic that we discuss, and it has to do a lot with linear time invariant systems. And you see that in every fMRI paper that basically says something like GLMs were created by convolving our stimulus onset functions with the hemodynamic response function. And usually it does not really get quite clear what the stimulus onset functions were, how many regressors then the design matrix, and what's going on. And this is just a sign of bad paper writing and bad review. So if you don't feel that when you read an fMRI paper that you can draw the design matrix that people use, then the paper is just crap and you can just throw it away, because it's a waste of everybody's time, because you don't know what's going on. So it's actually best to include design matrices as supplementary figures, so that you actually know what they use as a model, because if they don't know what they use as a model, how are you supposed to understand what they did? Anyway, the stuff that we want to discuss today are first level regressor formation, or the first level regressors. And this now taps into the discrete time system theory and linear time invariant system theory. So we have to understand what's going on and how this whole thing works. We have to again talk briefly about sequences. We talked about sequences previously, and when we talked about Fourier transforms, because they're our data, the stuff that we transformed by means of Fourier transforms, or for which we formed the Fourier series, were always sequences. So these are the same sequences, but we have to talk a little bit more about them, and also introduce the unit sample sequence. So that's the first thing to discuss, because this then relates closely to impulse response functions / hemodynamic response functions. Then we have to introduce discrete time systems, which basically are a fundamental building block of engineering work. So discrete time systems, or systems in general, are what engineers always deal with. So that's language from that part of the human culture. Exactly, that's the biggest word that I couldn't think of. Human culture. This will then allow us, once we talk about discrete time systems, and specifically linear and time invariant ones, that will allow us to talk about convolution, and then make explicit what this process of going from stimulus onset functions to predicting R series means. And once we have established that, we can actually look at some examples from fMRI, and this will also cover then the canonical hemodynamic response function, which is always called that in fMRI papers, and but is hardly made explicit what the function actually is. And then we can look at some convolution effects. So that's the plan, and now we still have some time to get started, which is good. So we're going to again address this whole thing from a mathematical abstract perspective, and then so start with fairly general concepts, and then in the end make things explicit for fMRI, because that's essentially what this whole fMRI cognitive neuroscience business is. It's just a special case of many fairly general and fairly standard concepts. Good. So first we have to remind ourselves of sequences, and that we've seen before. So essentially a sequence is just an ordered set of numbers, and there are different ways to write them. Here I write them like this. So X is a sequence, and X has elements which are called Xi. And the thing with the I is that I can essentially be a lot of things, but it needs to be discrete things. So one can have finite sequences where I, for example, goes from 1 to 10. Then the whole thing would be a finite sequence, and it would be 10 values that have a specific order and are indexed by I. So these is exactly the same as our sequences in Fourier analysis. So they were called nth order sequences. Then one can allow for I that I is a natural number, so that would imply that there are infinitely many elements in the sequence, so the sequence is actually infinitely long. In what we are discussing now, we also need to go basically into negative time. So what we are allowing for is I to be an integer. So I basically, just to remind you, runs from minus infinity to plus infinity. So this is the I, then one can, if one wants to be mathematically a bit more precise, one can actually define sequences of functions that map integers onto real numbers. Then one has a function definition of sequences, but one can do that, but it doesn't really help us much. So for us, currently it's fine to just think of a sequence as an ordered set of numbers. You can also think of them as vectors if you want, which is actually quite natural if you think about sequences and the GLM, because the sequences that we are talking about, of course, our Y, our data, YRN, is also a sequence. It's a finite sequence, so there are n entries, but the order matters. So in this sense, one can also think about sequences in terms of vectors. What we need here in the beginning is a little bit the idea of a sequence as an infinite thing. So there are different ways to think about it. So one way you could think of, or give an example for a sequence is as follows. So there are a lot of values before x minus 3, but then there's x minus 3, x minus 2, x0, x1, x2, and this, for example, could be defined as, let's come up with some numbers, 5.2, 3.1, 2.0, so that's now x minus 1, then x0 could be, for example, be minus 1, x1 could be minus 2.2, and x2 could be minus 7.3, and so on. And if you want to imagine these things as vectors, feel free to. So the only thing that I would then usually think of is as columns. So yeah, maybe have kind of a thing that looks like this, so and so on, and it's an infinite thing. So that's a little bit different from actually vectors. One can of course do also linear algebra and vector calculus with infinite things, but that's then more functional analysis. But yeah, intuitively, whether the whole thing stops here as a vector, so because there's like a 10 and there's a 11 down here, then it's a finite thing. If you have some dots there, it's going on forever. So yeah, but these are the entities that we're dealing with, sequences, and one needs to pay a little bit attention whether a sequence that one is dealing with at a specific moment is finite or infinite, but otherwise it's just an ordered list of numbers, like the data we acquire for a single voxel with fMRI. What we need in addition today for sequences, which we didn't need before, are sequence operations. So one can also calculate with sequences or compute with sequences. And we are specifically interested in two operations on sequences. One is sequence addition, and the other one is scalar multiplication of sequences. So these are the two sequence operations that we need to introduce convolution and everything else. Oops, not scalar operation, but scalar multiplication. And this is luckily fairly straightforward. So if you have two sequences, and I'm not saying what kind of sequence, so it can be infinite sequences. So if you have two sequences, x and y, with the elements xi and yi, then you can define a third sequence z as x plus y. So you add two sequences, potentially two infinite sequences. They need to be of the same kind, so you cannot add an infinite sequence to a he could define something that gives some meaning to what it means to add an infinite sequence to a finite sequence and so on. But what we are concerned with is always that we have two sequences of the same kind, so either two finite sequences or two infinite sequences, and then we add them. And then the question is, of course, what the elements of the remaining of the resulting sequence are, what the Zi are, and the operation we define here is element-wise. So the ith element of Z is given by the sum of the ith element of the sequence X and the ith element of the sequence Y. Yeah. So this is fairly simple. So if we have two sequences which are in this case finite and have three elements, like this is our X and our Y is 0, -1, 3, then Z, X plus Y has which elements? What's the first element of Z?
2, 4, and
9. Exactly. So that's really an element-wise thing. So it's straightforward. Scalar multiplication is also straightforward, maybe even more straightforward, but the important thing is that what one actually want to make this nicer. What one actually combines in scalar multiplication, and hence also the name scalar multiplication, is not two sequences. So we don't multiply sequences, but we multiply a sequence, X, and a scalar. And scalars is a little bit of a strange term, but what scalar always refers to is single elements. So in a way, yeah, just a single number. And you have scalars in various domains. It's always a little bit strange that a scalar in linear algebra, when it refers to vectors, is called a scalar, and when it refers to sequences, it's also called a scalar. It's interesting what a scalar really is. I don't know. But what scalar multiplication then refers to is to multiply a sequence X with a scalar. So A times X, that's the scalar product, which results in a new sequence Y. And the elements of these new sequence Y are defined as the products of the elements of Xi times the scalar for all I in Z. So for example, if we have one sequence here, 1, 4, -2, 0, and we have the scalar 2, then we can form the scalar product 2 times our sequence here. And what do we get?
-8, -4.
-4, 0. Exactly. So these are the two operations that we need so to be able to calculate with the sequences. So we know what sequences are now. So ordered list of numbers, usually real numbers. And we can do two things with them. We can add them and we can multiply them with a scalar. And does anyone of the mathematician remembers if we have a set and addition and scalar multiplication? What is this? Is this a ring, a field, whatever? It's something. Hubble group. Anyway, doesn't really matter. But this is a lot often what you can always. So you basically come up with a set and then you define some operations on it. And if these operations fulfill certain conditions, you have created a mathematical entity, and like a group or field or something like that. It's not too important, but it's a very typical mathematical thing. So these are sequence operations, and then we need another thing to get started on systems, namely the notion of the unit sample sequence. And the unit sample sequence, question? No. The unit sample sequence, there's actually not only one, but so the way I'm doing it now, and I hope it works until the end, is that there are k, and k can be an integer, or k is an integer. So the kth unit sample sequence is denoted here by delta, and has a little superscript k, and is defined as follows. It's a sequence, and hence it has elements, or components, elements, whatever you want to call them, delta ki, and these delta ki are defined as follows. Delta ki is defined as 0 if I is not equal to k, and 1 if I is equal to k, for all I in z, and this whole thing is also defined for all k in z. So this little thing here just means for all. I usually avoid using it because it looks fairly technical, and for me it is a little bit like, I'm a mathematician, I use this, and I use this, I'm a mathematician. But you can just say for all. So an example for the unit sample, for kth unit sample sequence would be the following. So it's infinite, and then we have, let's say, delta. Let's do delta 0 because this is an important thing. -2, -1, delta 0, 0. Delta 0, 1, delta 0, 2, and then it's going on. And so can you tell me what these are if we write them out, what these values are? So of course we have a lot of values before that we don't talk about, but what is the value of delta 0 and -2? If you look at this here, this. And as you started, you can go on.
0, 1, 0, 0.
Yeah, exactly. So whenever whenever the subscript is not equal to the superscript, the entry is 0, and if they are equal, then the entry is 1. So the 0th unit sample sequence, so the delta with this little superscript 0, has a 1 at the index 0, and zeros everywhere else. Just to make this with the k clear, we can also look at another example, namely, let's use, can't decide, it's too boring, it's boring anyway, so let's look at this. So who wants to say what these are? So starting here. Yeah, just go on. Yeah. next one 0, this one, and this one. Exactly. And all the other ones that we didn't discuss here are also 0. Yeah. So this is how the unit sample, the kth unit sample sequence works. And before the break, let's look at one more thing, because that's important also for the rest. With these unit sample sequences, one can express sequences as follows, and this will be important for the remainder. Expressing sequences, expressing sequences as sums of k unit sample sequences. And this is essentially this one equation. So if one has a sequence x with its elements xi, one can write this as the infinite sum of the elements of x, so the xi multiplied by ith unit sample sequences. So what this means, or the way to interpret this, or the way that I look at this, is as follows. It's easiest for me to visualize this in vector form. So x is in general an infinite sequence. So let's say we only look at the entries -1, 0, and 1, and it goes on. And this can be written as an infinite sum, and we don't look at a lot of them, but we look at some of them, essentially 3. X, and we start with the ones that we are given here. So we have x -1, and then we have actually here, this is a scalar product of the ith entry of the sequence x. So that's a scalar. It's just this x -1, for example, 3 or 2 or minus pi or whatever. Or minus pi, okay. And it's multiplied with the ith order, so the ith order unit sample sequence, which, as we established previously, has a 1 at the -1 entry. So ith order, I is -1, so it has a 1 here. And then for 0 it has a 0, and for x1 it has a 0, and then it goes on. Then we have our x0, again a scalar product with the 0th order unit sample sequence. So we have a 0 here, a 1 here, and a 0 here. And then we have another sequence here, which is a 0 for -1, a 0 for 0, and 1 for 1, because we have the delta with a superscript 1. And then we can essentially form, multiply them. So then we get x -1 here, x0 here, and x1 here. And then we can add these sequences, and then we get these sequence back. Yeah. So this is my interpretation of what it means to express a sequence as the sum of kth unit sample sequences. So we are adding the scalar multiples of, in general, infinite unit sample sequences, and the scalar products are formed with the elements of x. And then if we have these infinite sequences that at their respective entry have exactly the same entries as x, and if we add them, then we get this back. Yeah. That is a little bit the question, why do we do that? I mean, it's completely redundant if we look at it this way, but it will make sense once we look at convolution, and once we apply operations to sequences, because we want to, maybe as a teaser before the break, we want to basically input these kind of unit sample sequence into systems like the brain, neurovascular system, MR signal, and then look at the output sequence. This is what is called impulse response function or impulse response sequence, which is then the same thing as the hemodynamic response function. And we want to look what happens if we put in different signals. So this is why we will need this. At the moment, it's completely redundant, but it's possible. That's the only thing that we know now. Okay, then let's have a break. Start 5 minutes after 9 with discrete time systems if there are no questions right now, which I can't really think that.